All right, so last time I was talking about different types of testing. I didn't quite finish the fuzzing slides. I'm going to start over with fuzzing. Fuzzing is, like I said, it's random testing. It's taking your program and throwing a whole bunch of stuff at it and seeing what it does. And there's lots of different ways this works. And a lot of ways it doesn't work. And so, like I was showing you the charts and graphs earlier, where they're only covering 40% of the code, 30%, actually it was 15% of that one example. Because a program requires specialized input of the right format. If you're doing a PDF viewer, it requires it to have the PDF header in it to tell you it's a PDF file. It has to have, and usually the program looks at that and says, that's wrong format, wrong input, I'm not doing this. Sometimes the program doesn't do that because we expect the user to give what we asked them to give. You know, and it's a common thing among developers and engineers. Well, I told them to give me a number. Why nobody would reasonably not give me a number? You know, and I've heard people say things like this too. It's like, but if they did that, it might crash the program, and they want the program to work. Usually, but there are people who want to crash your program. People who don't want things to work. But like I said, and some parts of the code won't be hit by the fuzzer because they require, you know, you select a menu option, and then you do something, then you enter a certain name or value, and then it goes in. You know, if I'm looking at a viewer of something to look at different images, there's code that'll show me a JPEG image, code that'll show me a movie, code that'll show me, you know, in movie formats, you got MPEG or MP4, or you got the AVI, you've got the MOV format, you got all the different file formats. Different parts of the code interpret the different files. If you don't give it a file of the right format, it'll never hit that part of code. And fuzzers don't do well at that. What we have found is we have a good test suite that tests most of the code for us. And so it has all the right formats. And then we just make tweaks to that, the test suite, and see if, okay, what if it was slightly formatted differently? Would something crash? And so there are fuzzers that use that, and that we call that their test corpus. It's the test suite that they bring things in. So like I said, and I never fixed this still. Traditional fuzzing is a black box, random inputs. Smart fuzzing guided by other techniques. Like, hey, here's how you do create HTML, XML, PDF files, whatever. So it helps to have that information. Question is, do I have that right information? Well, it depends who's doing the fuzzing and why. If I am testing code I am developing, I know what it should do, and I have all the right file formats in all my test suites. If I'm testing code I'm not sure about that I've downloaded from the internet and I want to just see, should I use this? That's a different story. So it's really good for developers because they know everything. They have their test suites. They have their standard way of testing, and this just helps enhance that. Okay. Now, broadly speaking, fuzzers fall into two categories, what we call generation-based fuzzers, which they generate input from scratch, possibly with knowledge of the expected input format, and mutation-based fuzzers, which generate inputs by changing or mutating known valid inputs in some way. So it's oh, hey, so when we did the Cyber Grand Challenge, Dr. Song wrote a fuzzer. We had network traffic, so copies of messages being sent to the programs under test, valid messages. And so, and these were all text-based messages. Actually, they weren't all. A lot of them were text-based messages. And so she would see, okay, a string, space, a number, space, another number, or comma separated or whatever. And, oh, wait, there's a number. Well, I'll replace that with a really big number. I'll replace it with a negative number. I'll replace it with a random string of letters. And, you know, just mutate those things and see what happens. And so I think the latest version of that fuzzer, you know, there's 255 programs. She could crash 90 of them just doing this type of mutation. I think it was 90. It could be more. So the mutation, like I say, you take a well-formed input, randomly mutate it. Maybe just flip a single bit. Remove the null. So Strings in C, like I said, end with the null character, the 0 character, to tell us that's the end of the string. What if you remove that from the input? How does it know that it's the end of the string? Yes.
So if others or any of these programs break the program, does it generate some sort of a report? Because these things are going through lots of iterations.
Yeah, the fuzzers generate a crash report.
Okay.
And basically in the crash report is a copy of the inputs that caused the program to crash. And then what they can do is save those and use that as part of the corpus for the next time you're testing the program. Also, what they do is like, okay, fix the program. Let's rerun it. The first thing it does is run through all those crashes. Then it tries to tweak them a little. So that reminded me of I don't know why that reminded me. But thinking of the Cyber Grand Challenge when we did that, and I talked about this earlier, but basically we were given a program and we were trying to crash it. The way it was set up, when we were running it on their test suites, is we sent them, let's see, what did we do? We sent them our program and they ran it against their programs to see if it would crash. And one of the programs was crashing in an unexpected way. And they couldn't figure it out. And it was something we sent. And so how this works is you send a message to their program over the internet, their program executes, and then sends a response. You read the response and maybe that tells you what to do next. That's the normal way it works. How they were simulating this is we sent them a message in a buffer. They wrote the output in the buffer and it just sat there. So buffer and a place in memory until we read it from the buffer. It wasn't actually sent out over the internet. Well, our attack was slam everything out you can. Read, nah, who cares about the responses? So we never read the response. So their program kept sending responses. What we did overflowed the output buffer because we never read it. And they're like, how could you attack a program without ever reading the outputs? That makes no sense to us. We said, but it worked, didn't it? And they're like, yeah, but the guy was so upset that he didn't think of that as a possible bug. And in several of these programs, these test programs, they wrote the code, they inserted certain bugs, and people found other ones. Because the developers who were writing these things still wrote bad code accidentally. Because they think, well, nobody would ever do this. Nobody would ever not read the output from my program if they're trying to crash it. Why not? If I can make your program do what I want it to do without. Now, granted, we couldn't make it do what we wanted to. It just overflowed the output buffer. He was controlling the contents of the output, so we never could do anything about it, but it was still annoying to him. It was a denial of service attack. So anyway, mutation-based, we have little or no knowledge of the format of the input. We just know what they look like, and we change them. Super easy to set up, super easy to automate, little or no protocol knowledge required. So it works on a wide range of programs, limited by your initial inputs. If you don't have the valid set of possible inputs, you can't run the output. So just think about these things when you move on and do your own testing and developing in the future. The generation-based fuzzing, test cases generated, like I said, from some description of the format, maybe a specified network protocol, maybe a file format like XML, PDF, MP4, whatever. Knowledge of the protocol should give you better results than pure random fuzzing. The biggest problem we have with fuzzing is it runs, the program says, yeah, that's not a valid input, terminate, or send you an error message. And basically you're wasting cycles, you're wasting time trying to figure out what to do. The strengths with this is its completeness. We can get much more detailed inputs. We can get further into the code, get more code coverage because we're trying all those test cases, deal with complex cases. But you have to have certain knowledge of the program you're testing. If you don't have that knowledge, it doesn't work. Writing the generator can be labor intensive for complex protocols. And people don't want to do that because, hey, that's not the code I'm selling. So how much fuzzing is enough? Well, mutation-based fuzzers may generate an infinite number of test cases. When has the fuzzer run long enough? Generation-based fuzzers may be limited and give a finite number of test cases. What happens when they're all run and you didn't find any bugs? And so one thing the community's looked at is code coverage. Have I covered all the code? Maybe that's enough. Have I covered a significant amount of the code? Have I run long enough? If I can't find it in this long, the bad guys aren't going to. So like I said, code coverage is a metric used to determine how much code is executed. There's a test coverage program, a GCov, GNU coverage. So GNU, okay, let's go way back. Unix was the original operating system, or an operating system in the 70s that a lot of people started using in the research community. AT&T Bell Labs took Unix, license from Berkeley, modified it, and then were making it available to people. And then they started saying, nope, you got to pay for it. And people weren't happy with this. They wanted free operating system because they were used to it. So Berkeley started redoing it and creating the Berkeley standard distribution of Unix. Linus Torvalds started working on this and saying, I'm going to create my own. That became Linux. His was later. GNU is the a group of the Free Software Foundation that wanted to create this. GNU, GNU stands for GNU's not Unix. It's a recursive self-definition. So we have a lot of G things. GCC, that's GNU's C compiler. GCov, GNU's coverage. They actually don't have their own version of Unix anymore, but they have a lot of other tools that we use that are all part of the G suite. That's all free. So anyway, GCov is a tool you can use in conjunction with GCC or with this, the Clang C language, compiler Clang. You can do, it generates the coverage tools. And then there's ways of running it. You run your test program and it says, hey, you ran your test program, it stores the output file. These are the lines of code you touched. And then you can look at it. And it tells you maybe which functions you're covered, or which lines of code are covered, which branches, because there's different pieces of your code are covered, which sections of code are covered, which execution paths are covered, all these things. So these things exist, they take a little time to run. You also have what we call profiles, so gprof. The G profile tells you how much time you're spending in a certain function. So I'm running it, I'm not getting much coverage, and it's stuck in this one function doing lots and lots of stuff. Maybe that's not the place I want to be testing. And so here, if we have a so if we have, you know, a test case, if X is greater than Y, we do true branch, otherwise we do the false branch. And we make different assignments. And then if M is greater than N, we do a true branch. We want to test all these branches and all these paths. So we got X is greater than Y, yes or no. M is greater than N, yes or no. So we should have the 4 cases: true, 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 false, false, true, false, false, to hit every possible branch, every possible set of cases. Now, some people may say, no, it doesn't have to matter. We just try these, both of these with this one being true. Both of these with this one. Well, no. And then we're fine. And then just try, or maybe just try true, true, and false, false. But it could be a false here sets up something that's true, causes a problem. Well, this is a very, very simple thing. And you already got 4 test cases. How many paths do you have? What if there's a loop and you go back and do something again? Is that an extra path? If this was inside a loop, do we have to do true, false, followed by false, true? True, false, followed by true, false? You know, do we suddenly have now not 4 cases, but 16 cases? You know, and these are things we have to look at when we're, path coverage usually doesn't worry about that. It looks about the single path, it doesn't worry about loops. The code coverage that people use tells how good the test is, how good your test files are. You compare different fuzzers, you can identify paths through the, you can compare different fuzzers with different coverage, which one did better coverage. And I kind of showed that graph earlier. Identify paths through the code that may have been missed. And can use to guide your fuzzer. Sometimes they say, hey, I get to this if then else, and I'm always taking the true branch. Let's find a way to change the inputs to create the else branch. Now, in the CyberGrant challenge, when I was talking about it, some of the teams actually did that. They had internally a mathematical analysis that kept track of all the values. And so they said, oh, X is greater than Y. Y was, they said, created a symbol for it, put it into a logic analyzer, a satisfiability solver, and said, is there any input that affected the value Y? How can we change those inputs to make Y greater than X? So we can get this other branch. And so they created long, complex equations showing, hey, given these inputs, and all these computations we performed on the inputs until we got here, what could we change in the inputs to get this right output? That's, in general, it's an undecidable problem, but they can run it for a while on these satisfiability solvers and see what happens. They usually ran it for a certain amount of time before finally they said, hey, we're done. We didn't try to do that. I think it's an interesting exercise. It's a lot of work to code it up. But some of the fuzzers build that in now. So we use what we call symbolic execution, run the program until you're there, say what the user input is, this symbol, this random thing. Let's figure out what we can do. Okay. Problem code could be covered without triggering bugs. We can actually go through a piece of code that works fine because the inputs weren't quite the right inputs. You know, it needed a negative number to cause a crash, and we always gave it positive numbers. Well, it went through that code just fine because we never put in that negative number, and it never noticed it. And how could that happen? Well, that's exactly what developers do. They run a bunch of test cases and it doesn't crash and they think they're fine, but there are edge cases that cause the problems. So AFL, American Fuzzy Lop, this is what the output looks like when it's running. And I'm just to show you an example here. So, and they recommend running for 24 hours on a single program. They have different types of fuzzing strategies, bit flips, byte flips, arithmetic, so make it positive, negative, other things, known integers, maximum negative integers, etc. Havoc, which does a bunch of random stuff, and trim. I don't even remember what trim does. And so it just tells you, what's it's trying, how many executions it's done. So this one, let's see, where are we? Yeah, so this is run 654,000 executions of the program. It does 2,306 per second of this program. It has a map coverage, so far it had covered 7% of the code. It chose looking at different paths, covered 65% of what they call the favored paths, created 43% new edges. But here's the interesting thing. One time the program hung. And what they mean there, they have a certain time limit, said run your program for this long and then stop. If the program doesn't normally terminate, or if it's not responding, it's hung. They found that once. Unique crashes, this one so far found 0. But tells us how unique ones it has, and then 195 total execution paths. And this had been running for 4 minutes and 43 seconds to get the 654,000 different test cases run. And it can run in parallel and do other things. And so this, you run it, you can run it in the background so you don't see this, or you can pop it up so you show the screen and you just watch it run. And it's like, yeah, the numbers keep going. And there are ways of having it say, hey, run until you get 20 crashes, then stop. Run until you get, usually when I do it, I say run until you get at most, run for a certain amount of time or 10 crashes, whichever comes first. Because there's one program I've run this on, I will actually record a demo of it running, which is a really simple program written by a freshman in a freshman level class that has a major bug in it. So it's real easy for this tool to crash it. Thousands and thousands and thousands of times. And I don't want, hey, I've run it for 10 minutes. I've created 10,000 crash files. I don't care. Just a couple of them will be sufficient. Thank you very much. Yes.
So you've ran this for 5 minutes, essentially. You talked about other fuzzers running for days or something. Kind of what's the typical run on?
The community believes you should run for 24 hours. And that's just what they said is when we compare the usefulness of fuzzers, when we're testing them, when we're testing advanced pieces of code, they say run it for 24 hours. Some people want to go further depending on how critical your code is. Others will say, yeah, you run it for 24 hours every time you do a build. Well, if you're doing nightly builds, you're running it constantly. There are lots of different fuzzers out there. There are, and people are trying to figure out how good they are. So there's OS fuzz, which if you set up things correctly, Google will run your fuzzer for you against a certain open system software to see if it'll work. So one way, it's a way of testing your fuzzer, but the other, it's a way of testing the open system software. And so there's a lot of people now, I think, yeah, with OS fuzz, the idea with OS fuzz is to create open system software, free software. You put it up there and Google will keep throwing all these fuzzers at it constantly for free. Then there's Fuzz Bench that goes the other way. There's a set of the 20 different programs that they have known bugs in, and then they run the different fuzzers against them. So, all right, any questions? So Dr. Song will go more of these in Cyber 220, or whoever's teaching Cyber 220, because most of you won't take that next semester. I don't think any of you will take it next semester, but we'll see. Oops. All right. I'll just move on to web security section. So a lot of what I do personally is I look at programs that run standalone on your computer. A lot of network utilities, a lot of or programs that are running in the background and doing things. But a lot of people do things and run web apps. And so we need to pay attention to that. What's interesting, is what do I mean by web app? I should ask that first. Any idea?
Google Docs.
Google Docs. Okay, there's a web. So how does that work? From a user perspective, I go to a website, I open up my document, I can edit it on the website. What is actually running there? So I've got my browser running. I have gone to their website and downloaded some code onto my machine. And that code is executing inside my browser or on my machine, but it's executing on my machine doing things. That's called a client-side app. My machine is the client. I download things, I run things. Then it sends information to the server. You know, your Google Docs, you've updated the document. Well, the server needs to know that and store it on the server in the cloud so that somebody else who's accessing that Google Doc can see it. There's an application running on that server, a server-side app that is running and doing things. And so when we do web app security, we definitely want to test those server-side apps. Do we need to worry about the client-side apps for security testing? Depends why and what you want to do. If I, on my computer, attack and hack the client side app running on my machine, I will get into and hack my own machine. Who cares? Right? If I attack the server app, I can get in and hack the server. Yeah, we care about that. And this is the mindset a lot of people have. Also, I can go in, I can look at that code I downloaded and modify it and do whatever I want with it. And so, or I can intercept the messages being sent and send your server different messages. I can do lots of things to spoof the server and fake the server. What I do worry about as a client is what if that client-side app is bad? If that app is malicious and it's coming into my computer and it wants to attack me on behalf of the server. That's a different problem. I'm worried about that. Usually I'm worried about my browser allowing that client-side app to attack me. But some people just scan the apps and is this malicious app? Does it have bad code in it? Is it something that might attack me? So different points of view, and you got to think about these. You know, just like I tell people when you do computer forensics, your computer is either the victim of the attack, your computer's been attacked, and we want to analyze what happened, figure out how they got in, what they stole, what they changed, and fix it. Or the computer was the weapon in the attack, it was used to commit the crime. I launch them. So if I take somebody's computer in an investigation and I want to analyze it, I'm analyzing it to see what they did. There's a third part of it where the computer is just a tool they use to keep track of their ill-gotten gains. They have their spreadsheets and documents and images and other things that are evidence in the crime scene, but it's just more a media storage than anything else. So people look at things three different ways. And same thing when you're looking at the web apps. Am I worried about being attacked? Am I worried about my app being attacked, or the app attacking me? So most of this worries about your app being attacked. I've created the app, I'm selling it, I'm marketing it, I don't want to be attacked. I don't want my website attacked. If I have a pay for service, you get in and you look at, you can have access to all these different files, services. I can stream down the current all NFL games, but I got to pay for that. Can somebody get in for free? Can Google Docs, can I go in and go into your account and mess up his doc? Access it, read it. Can I change content on a real website? Make it look different. It's a website defacing, that's an easy. There's bugs in the web. There's something called clickjacking. Does anybody know what clickjacking is? Yes.
Is that when you overlay a link on something that looks legitimate so that it redirects you somewhere else when you're thinking you're clicking on something?
Yeah, effectively, you overlay something hidden. So I click on what I think is a valid link, an approval link or whatever, and instead I'm clicking on something else and it's redirecting me somewhere else, approving something else, downloading something else, etc. Drive-by download, just looking at the website, it'll download stuff to my computer and then do things. There's several others that we have to worry about. I'll talk about some of those. So, hey, there's some important things you want to read. You go to a website. Hey, studies of low order even primes, how to cheat at solitaire, making anti-gravity paint, and what to store it in. That would be a problem. Yeah. 101 things to do with string. These are files that somebody might want to load, not a link. Oh, hey, to read these, you need to download Acrobat PDF Reader. And that's the thing that's infected. To access this, you need to click and download this software. Have any of you ever done that? I have. I've done it a lot because there are things I need to lose. Usually I don't follow their link, I do something else, but sometimes I don't. All right, a web bug, a clear GIF, a tracking bug is a tiny image as small as 1 pixel by 1 pixel, not normally seen. Here's little examples of them. Loaded and processed the same as the larger picture. Notifies the bug owner that the user has loaded the image. And so it's just saying somebody has accessed this file. It's a way of tracking what you're doing. Now, the way websites work is when I access a website, every image, actually, let me do this. I'll just go to, let's go to, that's not what I wanted. There we go. There's a search browse. Let me share this. I think I may have shown this before, but so like here's a, hey, I highlighted on something popped up. I've got links that do things. This really is this. Okay, and this is just part of it. But we have some JavaScript in here. We've got links. And when this goes through, this says, hey, download this JavaScript and do certain things. But if we have images, these are different images we want to grab. Each of them has a different reference, a different location on the internet where that image exists. Each of these, the computer goes and downloads those separately and independently. I will download this, and now I figure out how to display it. I will download this. So the whole idea behind this web page stuff is every image is downloaded independent and separately from the others. These links are stored, and when I click on it, it goes somewhere else. But often I download dozens, if not hundreds, of individual things to piece together the page. So dynamic content creation. And so when I create this web bug or create something else, it's a little image that is just stored and rendered on the page, along with everything else. It can be downloaded from somebody completely different computer. You know, I get sources. These things live at different places in the internet. Most of these should be from U of I, but some of these aren't. And the shop related products, you know, and the other things I can get, Boise State, that's not on U of I. You know, comes from somewhere else. You know, the Bing videos they made, these things trending on Bing, these come from somewhere else. These come from Bing, they don't come from U of I. You know, of course, I'm not on U of I's website. There's U of I's website. You know, these are our images, these things, but these images are stored on servers somewhere. So we download these small things, overload them on the images. We get these, we say, hey, somebody visited from here. Another visit from here. You know, we can send them a targeted ad because now we know, hey, they've downloaded these two images, their computer. There's things called cookies that are small bits of information when you download something that's stored on the machine to keep track. My server doesn't want to keep track of things that every single person who visited my server in the internet has done. So I send to say, store that little information on your computer in this little cookie. Well, now I can ask the computer when I download something, retrieve that cookie so I get the right content. And so we can do a lot of different things. A lot of this is legitimate. A lot of this is used for the standard user, but it can be malicious. So we'll talk about some of that. So clickjacking, like I said, you know, here for a free pizza, click here, and this overlaps. Do you want to perform this dangerous act? And you click here and you hit yes. You know, it looks, they make their input dialog transparent, place an image below the transparent dialog that looks good. User ends up answering a question they didn't know they were being asked. Like, do you want to install this software on your machine? Yes. I thought I was getting free pizza. Like I said, drive-by download codes downloaded, installed, execute on the computer without the user's permission, without the user's knowledge, unwanted browser toolbars. Now, one way this happens is drive-by, you just go by and download it. Another way is you download, like if I download the latest version of Acrobat Reader. If I don't say no, it installs a Yahoo search engine for me or something that I don't really want. When you install, you know, download code from somewhere, or used to be when you had it on a disk, it has other things that installs with it, that advertisement and stuff that you don't necessarily want. But this is, I just go to a website and it downloads things for me. I don't want that. I was experimenting, I heard about one, so fortunately I did this in a virtual machine, experimented. Set everything up the way the person said, went to a website, and it inserted a bunch of things on my calendar. That saying, you know, whatever, there were different meetings or something. And so if I clicked that meeting, I revisited that website again and again and again. I did it once a week for 2 months on my calendar and in a Gmail calendar or whatever. And all this fortune was a fake Gmail account, fake everything. So I could just get rid of it. But it was JimAF testing at gmail.com or something like that. JimAF spam at Gmail. I use a lot of those. Create them, test them, throw them away. Oh no, I don't do that. That violates the permit. No. I can obtain user or website data. You know, one thing is useful if you go back to the website. I have to go back to this one. So if I'm on this website, this address matters. Right? If I click on academics, you notice that this puts /academics in here. Well, I can do .. it goes me back to the beginning. In Linux, when you're manipulating a directory, .. says go to the parent directory of the file. To .. says, hey, I'm down here, I'm down in academics. I've got that. I request info. Okay, now I'm at admission/RFI, and I can just type whatever I want. But if I go back up, I'm back up to admissions website. There may be a hidden parent website, and they're assuming only what you're accessing, everything below it. Well, if I manually type something, I go up. It didn't know I could do that. The developer was thinking, well, nobody would do that, so they didn't bother putting protections on it. And so that's just one minor thing, but that's forceful browsing, we call it. So I can go and just make it do whatever I want it to do. So the .. is directory traversal. CD ... go to the parent of the current location, CD ... go to the grandparent. Most commonly entered into the URL bar, but may be combined with other tags. So yoursite.com, web hits, this type of thing, file equals, this is the file you wanted. I make it go all the way up to the parent directory, WinNT system 32 autoexec.nt, and get to download that and see things. There might be information in there. There might be default passwords, default user logins, other things. Maybe there's a script down there that tells me, the server-side app script, and I want to look at it to see if I can find vulnerabilities in it. So I manipulate it, so I download it. People know how to do this. So unless you have your server set up correctly, say, no, they're not allowed up above this area. They're not allowed in these files. You have problems. Cross-site scripting. Now, this is a type of what we call an injection attack. We put new information into the system. Malicious scripts are injected into otherwise benign and trusted websites. They occur when an attacker uses a web application to send malicious code, generally in the form of a browser-side script to a different end user. So a common way this is done, for example, is on a chat or comment section. You can see what other people post in response to something. Well, if they embed in that chat certain commands and the browser is not handling correctly, or the server's not handling correctly, let me phrase that. I type something into the chat that includes a command. I post it. Your server sends it to me. What my code sees when it's made up this whole website is your command. It says execute this. It's described, it looks like part of the website thing. So my browser will just execute it because it's not quoted out. It's not highlighted saying this is pure text. Show me the pure text. So I can inject things. I can do this now to cause you, put up a command and cause your browser to go to another website and download content from my website, send information to my website, pop up different alerts, pop up other things that you don't know about. Pop up, one I saw was pop up something that says, you need to log in again, enter your user ID and password. And it's a little dialog box. And so they type that in again and it gets sent to me. Thank you. So for example, scripts and HTML tags are encoded as plain text, just like the user input. So here's a google.com search, right? And maybe I just wanted to put that in somewhere. And instead I put in this script source, badsite.com/cross-site scripting JavaScript and script. And so this thing, when it's displaying it on the screen, will actually execute this thing. Because the browser is just going through reading these things. Oh, wait, hey, there's a script I have to read. Because your browser doesn't know better. So like I said, the attacker injects their malicious code to the victim's browser via the targeted website. So I do something on the targeted website. Sometimes it's, I can hack their website and post something in. Sometimes it's just like I said, put it in the comments. Let's see if I can. Is this actually working? Nope. Well, that was a weird one. Maybe I should be careful. Can you, I'm not sure. So assume a vulnerable service on a web server where cybersecurity is provided by the users. We could, where the user puts that in so they could do something, like I said, like script attack. So this is not going to work because it's just example, but I had links on one of these. Like I said, I will show you these actual ones. So HTTP GET request sent to the example.com web server, which returns a page containing the search result with the original input on the page. So if I can click on something, it goes to a server, it comes back and says, hey, here's the input, that part of what you put in, and I put in the script, you know, we got the attack. Example here, we got a user profile and a social network. It's a channel. It's set by one user, viewed by another. So Alice's account, you know, got Alice's information, Bob's information. We can take, so here's one that's Alice or maybe Sammy, puts information in the About Me section, and there's their script. Set the timestamp, secret token parameters, and all this. Create a request, add Sammy as a friend automatically when you view the browser. It just says, hey, I am going to add them as a friend. So when they click on the profile, it runs this code, this JavaScript code. It runs the code, it's not displayed. It sends an add a friend request to the server. As soon as it's loaded, malicious code also gets executed. So there are people who do this just to get their friend count up. Add it to your favorites. So suddenly you're now on their favorites list because you visited their site. Sammy is a cross-site scripting worm that's designed to propagate across MySpace social networking site, written by Sammy Kamkar. It was relatively harmless. It carried a payload that would display the string, but most of all, Sammy is my hero, on their MySpace profile, and then send Sammy a friend request. When they viewed that profile page, the payload would then replicated and planted on their own profile page, so that now when anybody visited their site, it sent Sammy a request and added this stuff. Within 20 hours, over 1 million users had run this payload back in 2005. Sammy had 1 million friends. You know, because it was a self-propagating worm. It was like, you know, the worm code was read here, put on Alice's worm page, and then when Bobby saw her profile, it was put on Bobby's page, et cetera, et cetera. So these communication channels overall are supposed to be data channels, give us information, but if they contain HTML markups, if they contain JavaScript code or other code, and because instead of being plain text data, the browser executes it. I'm just saying this again because browsers don't know the difference. If they look at it, they see this code, they say, oh, I'm supposed to execute this. This is something to do. Okay. The web server has to sanitize it appropriately, has to mark it up as this is not. Now, how do you do that? One way initially that people said is, okay, I get something from you, I'm going to put it in double quotes. So it comes from you, double quote starts it. The browser knows, hey, this is in double quotes, treat this all as a string. Don't execute anything there. And then when it's end, we end the double quotes. So you say, well, that's interesting. Okay, my name is Jim, double quote, script, etc. The program starts, sees a starting double quote, goes through, oh, the ending double quote of mine, finishes it, and then executes the script. Because I didn't go through and say, oh, if the user sent a double quote, change that to something else. Now we could change it to a command code. We can escape it. There's lots of ways, and then the attacker does one more level of indirection to undo what our sanitization was doing. Some people look at this and we're going to scan for anything that says script in it and just say, no, you're not allowed to do that. There are different ways of doing this. We just have to be careful. There is a way of saying, everything within this container is text. And no matter what happens, never execute anything in there and download that, put it in a text box on the browser. Browser people don't like that because it doesn't necessarily format correctly, but we just have to be careful. So what can happen with this? Well, the injected JavaScript code can make arbitrary changes to our web page, can change the news article page to something fake, or change some pictures on the page, change what's downloaded, can send requests to the server on behalf of the user, and that's where things get bad, or can steal information, say, hey, go back into my source machine, look at my cache, look at my saved passwords, look at other things. So one I know I saw somebody was trying to do was they were setting it up so it looked like a standard login. Somebody would, yeah, and it would request and put in their saved passwords for their login so that they can get those. Like I said, the approach, we can filter it, remove code from the user inputs. But there's many ways to encrypt it besides the script tag. So people first start, hey, we'll just look at the script tag. That'll solve my problem. Well, unfortunately, there's lots of ways of doing it. Part of the reason is we have multiple languages, multiple fonts or keyboards, so we can change things differently. Instead of implementing your own, there are some libraries out there, well-defined, well-vetted libraries that will filter out these things. You can replace your markups with alternate representations. Data contained JavaScript code is encoded before being sent to the browsers. The embedded JavaScript code will be displayed by the browser. So you convert script alert, for example, /script. So this says, you know, pop up. This basically is pop up something that's cross-site scripting to ampersand LT, which is this left angle brace, semicolon script, ampersand GT is this right one, alert. So we take the text they had and, like I said, replace all these symbols with something that the browser will still show and display correctly. It says display this, but it won't interpret it. And you'll often see things like that on the web browsers. And X0, you know, X20 or whatever, which is hex 20, which is space. And that's just to avoid somebody putting these things in. So the countermeasures to these injections: filter and sanitize all user input, account for every possible potentially valid encoding. That's a problem. We still would like to find a way to tell the browser, here's the whitelist of valid encodings. Nothing else works. And then only use the valid encodings. What happens is the server may do the translation for you into that valid encoding format. So the servers have to do this too. And it's not working. We keep thinking it's working. It's not working. People keep changing things. Don't make assumptions about the range of possible user inputs. Trust nothing. Check everything. Use access control mechanisms on the backend servers. And again, the demo I'll show on the post it for later, because my laptop wasn't working with the demo. SQL. SQL is a standard language for interacting with a relational database management system. Structured query language. I can request things from the database. Many web apps take inputs from users, and let's see if I can hide that. Nope. Just shut up there. We'll take input from users, use these inputs to construct an SQL query so the web app can pull the information out of the database. Username, the file I'm searching for, the product I'm searching for, and the product code so I can get the product description. They also use SQL to store information in the database. These are the things I've ordered. This is my profile information. If the queries are not carefully constructed, the SQL injection vulnerability is going to occur. Incorrect handling of input to these queries can result in severe vulnerabilities. So let's go over some examples. Oh, sorry. What happens if we talk about it in more general? It's a technique that exploits a vulnerability in the interface between the web app and the database servers. If my inputs are not correctly checked within the app before sending to the backend database. So let's look at some basic queries. All right, so select star from employee. Employee is the name of the database, the table in the database. Star says select everything. Ask the database for all its records, including all the columns. So the database stores things usually in something like this. We have a table name, employee. We have multiple columns. One is usually the key we use to search for things. So here we have an identifier, then we have their name, their employee ID, their password, their salary, their social security number, etc. I could say select name column, employee ID column, salary from employee, and it'll only return those three. And it usually doesn't return it formatted like this, but I'm just trying to show you. But MySQL is a program, structured query language, standard way of doing this. So I can ask for these things. Cool. It is uncommon for an SQL query to retrieve all records in a database. The where clause is used to set conditions for several types of statements, including select. Because besides select, I can say update these things in the database or delete these things in the database. So SQL statement where this thing occurs. So maybe select EID salary from employee where name equals whatever my login name was. So when I'm asking for something, I say, hey, here's my login name, Jim AF. And it says, oh, okay, we're going to select things about Jim AF. Maybe it's a set of orders. And so everything where the user placed the order was Jim AF and not all the orders of everybody. That's a common way of doing it. So in this case, maybe select star from employee, everything from employee where the employee ID is EID 5001. So it only gets Bob. EID is 5001 or name is David. And we get both. So in the user ID or David. So these are strings. This is a command. The name is the name of the field. So we have a well-structured format for SQL that we can break. What if I said where 1 equals 1? Well, 1 equals 1 is true. So select star from employee where true. It gives me all employees because this predicate that interpreted this and said, hey, I got true, always true. Oh, that's useful. And we could use the update statement to modify an existing record. Update employee, so update their table, setting the salary to 82,000 where the name is Bob. Then if I select star from employee where name is Bob, I now have the salary of 82,000 where it was 80,000. I just gave him a raise. Nice. MySQL also supports comments. Text starting from a pound further is comment to the end of the line. Also double dashes comment to the end of the line. Or slash star in inline comment star slash. This is just in here, so you can select star from employee, and this also works. That's useful to know. So typical web application, like I said, consists of these. We have our browser, sending requests to the server. The server sends results. We send things back and forth. It can construct an SQL statement to send to the database and get a result back, which then it can pass on to me. Okay. If the server doesn't manage these queries correctly, like I said, it can cause damage to the database or leak information. The user doesn't directly interact with the database, they interact with the web server. So here's a form where I type in my data, my employee ID number, and my password. And then it creates the website creates something. This is a form. The source for creating this form action, get data.php. So this is the server-side app or server-side script that is run when the user hits submit. This says to the browser, this is text. So not a number, just a string. And we're going to give it the name EID. This is a line break. So it says, okay, we're going to have an input type, create a text box, create a password box. When I hit submit, it creates this request because it's what we call a GET request. So it calls getData.php. The question mark tells it it's a GET request. It then says for this field, this EID field, put in what the user typed, EID equals EID 5000. For the password field, put in what they typed, password is password 123. This is what's sent to the server. The server then, the get data runs this and gets these as parameters where this application can say, hey, give me the EID, give me the password, and it does its checking. That makes sense? At the server in the getData.php, it says, hey, we're going to get this EID that the user sent. I'm going to get the password they sent. I'll store them these variables. Here, the variables start with $signs. I then create a new MySQL query to someone. I create the SQL injection, excuse me, the SQL query. Select name, salary, SSN from employee where EID is EID, and I put it in quotes. And password is password, and I put it in quotes. So it looks like the right request. Then I send it to the connection, the SQL query, and get the result. And if there is a result, I print it out. So I can do name, salary, social security number, row, whatever. Okay. This is where the problems occur. When somebody constructs this SQL statement using user input. Right, so the whole database is here. If I do select name this where EID is 5000, password 123, I'm going to get this one. Okay. And I don't have the demo open. Like I said, it wasn't working for some reason. Oh boy, so this may cause problems. What if I can force this to get true?
By true, do you mean like
1 equals 1. How would you think I could turn this into something with a 1 equals 1? My password, for example, I could say password 123 quote. So this would put the end quote here for me. And or 1 equals 1. And then another quote. And the quotes at the end. Oh no, actually, then what I do, that's right. So end quote, so password 123 end quote space or 1 equals 1 dash dash. And now everything else left here, and I could have done the user ID too. Everything left here is assumed to be a command comment. And so the rest of the line is commented out. So no, it doesn't matter what the user put in there. So login, effective ID, EID 5000, quote, space, or space, 1 equals 1. And I win. And as long as I win, I'm happy. And you're not. Now, SQL queries, you can have multiple queries on a line. They're separated by semicolons. So I do the first one, quote, semicolon, dash, dash, or I do a semicolon, whatever. And the next thing I put is update of salary. Now, what the system is supposed to do is only do things if I'm authorized. The problem is a lot of databases are set up, they trust the server app to be authorized, to have done the checking. Oh, I'm not going to send this update request because Bob, when he logs in, is not allowed to send update requests. So the server app will check and not create an update. And so the backside app database doesn't need to double check. It doesn't even know who's logged in because I'm not logging into the database server. I'm logging into the web app. I'm logging into the application server. The server is the one logging into the database, and the server is allowed to do anything with the database. And so this disconnect is what causes all these problems. All right, so I think the rest of this is going to be the demo stuff. Yeah, which I really have to explain separately. Like I said, I'm sorry, it wasn't working well. So I will come back and I'll record this and share it with you guys later. Yeah. Question?
Can SQL fields or fields that generate SQL requests be buzzed?
Be what?
Can you use a fuzzer on like?
Yes, people do use fuzzers on, and they assume the input, the backend is in SQL, so they fuzz with specific SQL type of inputs. Yes, that's definitely done. Now, how would you solve the problem? You block out, you make sure they can't do that backquote in my input. We want to sanitize the user input to say everything that they're constructing is their string. Now, there's different ways they do this. One uses fixed format requests. And so it says, we're not going to allow standard user input. We're going to fix text blocks. And so certain things aren't allowed. There's others, like you said, sanitize that escape out the backslash. There's still a way around that by putting a second one in. There's ways of doing just other checking to say, okay, I've got the user ID. I've got the database of all the user IDs. Let me just see if it's in there. Exactly what they typed in exactly matches what I want to look in before I put it in the where clause. So lots of different options people use to try and fix this. Yes.
Could you do something where when they're typing in input, it won't accept the, what do they call, double quotes?
Right. So, well, see, the problem is if I'm typing in the input, I'm doing that on my computer. I own my computer. I can force my program to bypass that check. I can modify things. I can just send, I can intercept what's going on over the network and say, this is what it's going to send as a standard request. I'm going to now send that myself from a different application. And because I own my computer, I own everything it sends and does. And that's the biggest problem is people say, we'll do the filtering on the user side. Because that's my code running over there and I wrote the code that they're running, so I know what it does and I know it's safe. But it's running on their computer and they own their computer. And bad guys lie, cheat, and steal. I actually set up one where what we did, it was very specific. Well, we saw the check function they built in to their program. So we had an intermediate application that as the program was coming in, we rewrote that check function to always say true. Actually, what we did is we added one and renamed theirs, so it made it easier, and then had that go to the browser. So the browser received a modified input file, didn't know any difference. It was all over the same connection. And then I had a student do this, and then it was responding. Just, why not? Hey, we can do this because I can put a filter application in there between my browser and the internet. And then everything else went through as if it was just normal. It was like a proxy server. So, all right, I'm going to stop there. Any questions, comments, concerns? Okay. There will be a few more things posted to finish up for the semester. Homework on this, the software security chapter and the this one, a couple quizzes. Now, technically, I'm not allowed to give you quizzes next week. The 10th quiz will be posted for this week. I will post other quizzes next week that'll be makeup quizzes that you're welcome to do, but you don't have to, but they'll replace the lower scores if you want.
If you get worse on them, will they still replace scores?
I will, so you will get the 10 highest scores. So I'm a little behind in getting those. I wanted some of those up earlier, but so that'll be up to you. Look on the web. There's some of you I sent email to. You didn't get all the homework done. Get it done.